Assalamualaikum and good afternoon to everyone, to our speaker, Mr. Konstantina from Delft, and to all the participants online. So today we will be having a webinar. Title is Application of Hydrochemical Traces as a Tool in Hydrogeology by Ms. Konstantina Katsanou, a senior lecturer in water quality assessment and monitoring at IHE Delft, Netherlands. Just a bit of introduction of our speaker. So Miss Konstantina is currently the senior lecturer researcher in the water quality assessment monitoring at Delft, and she received a PhD from the University of Utrecht, Greece. And she has extensive experience in water policy at the European level, working in river basin management plans and flood risk management plans, and currently now teaching at parts of master science program on surface and groundwater quality monitoring in IHE Delft. So without further ado, I let Konstantina to start the webinar. Thank you. The floor is yours. Atina, unmute your... Yeah,
yes.
all right.
Good remark. Thank you, Adam. Thanks also for the invitation. And let me connect the dots here. So my name is Konstantina Katsanou. I'm currently a senior lecturer at IHE Delft. Trying to move my slide. Yes. I'm going to give you a presentation of past research. The configuration of the presentation first relates to the institute that I'm working at the moment. My researchers, although Adam summarized a little bit what I'm doing, I will talk about hydrochemical tracers and how we can use them and what are the results that we can get out of that using case studies. And of course, I will wrap up my presentation and open up a discussion in case of any questions. So IHE Delft is located in the Netherlands, is the largest international graduate educational institute. It has since 1957 25,000 graduates from 190 countries. A number of PhD candidates doing water-related research, and we have projects mainly related to capacity development. We are, of course, under the auspices of UNESCO, and we are the only institute in the UNESCO family related to water. Now, some things about myself. I'm originally from Greece. I'm a geologist by background. And I studied my undergraduate and postgraduate studies are in Greece, where the geology is much more prominent than in the Netherlands, which is a lowland country. I'm currently based in The Hague. I'm working the last 4 years at IHE Delft. I have worked and lectured in different positions in topics related to water quality, hydrogeology, hydrochemistry, and water resources management. And I've worked also in a number of countries and with people from a number of countries. I'm very passionate about supporting women pursuing a career in geosciences. That's why I have an involvement in a number of committees about this particular topic. Now, let's move to the topic that we are here to discuss about, hydrochemical tracers. There are different classifications that we can use. I'll use a simple one, which classifies the hydrochemical tracers into 3 categories: the dissolution-related, pollution-related, and stable isotopes. Tracers, when analyzed in spatial and temporal variations, can give a number of conclusions and insights to the natural and anthropogenic factors that influence an aquifer system or a catchment, and of course reflect the land use, mineralization, and recharge of an aquifer system. Now, here is a table with different variables that can be used. This table can be really extensive or very short, mainly categories related to the physicochemical variables, major anions and cations and their ratios, gases and radionuclides, trace elements and heavy metals, rare earth elements and their ratios, isotopes, but also a number of variables that are related to human pollution can also be used as tracers to understand a little bit more about our aquifer systems. I'll start with examples from physicochemical variables. I will use examples for Germany and Greece, where I have worked in the past and where the geology, especially in Greece, is quite fascinating. So we see here an area in the central western part of Greece, where the geology is too complex, and we went there to study the area without having really a good background because applied research was not carried out in the past in this area. And I'll give what simple distribution maps of physicochemical parameters can give as insights for the area. Here, for example, we see the temperature of water and how this develops in the area. And if you can recall from the geological map, here we have the limestones, here we have the post-alpine deposits. So we have sediments of different ages from Holocene up to Neogene. And here we see that actually the recharge of the post-alpine aquifers is carried out by the limestone formations of the area. This is very prominent and leads to dilution when we look at the electrical conductivity of the area. And we also see that we have two zones of abnormally high temperatures, which point out to two geochemical anomalies that are already known in the area and relate to deep thermal water coming up along faults of the area. So let's see now how basic anions and cations can give us an indication. And here we see the different water types. And of course, the first water type is the same water type with rainfall, so relates to really fresh waters. And we see that along the recharge zones here of the aquifers, we only have this type of water, while in the areas where we have the known geochemical anomalies, we see that we have the other type, which is related to sodium, but also to sodium chloride. So those types are concentrated here, and we also found that there is also a zone here along a fault, already known fault, that also relates to these sodium bicarbonate waters, which are very common, and they are considered by the literature to be deep waters. So even with simple major anions and cations and using a generalized background of the area, we can make some, figure out a few things. For example, we see that the quaternary deposits, so both the Holocene and Pleistocene deposits, do have fresh water. The Neogene deposits do have form a different group, and they are enriched in sulfates in the area. And then we have in these two zones water emerging from depths along faults that are already known in the area. So the combination of distribution maps and hydrochemical plots led to a better understanding of the aquifers and gave actually information on the aquifers type, the aquifers extent and recharge mechanism, but also the relationship between surface and groundwater bodies. Because in this area, we also found that the local river water bodies created dilution, and this was well reflected from the electrical conductivity. The lithium and boron values that we measured, especially in the geochemical anomalies, were higher pointing out to this deeper water coming in the surface through faults. So let's see another example from major anions and cations. And let's move to the northwestern part of Greece, where the geology again is complex, but is related to a sequence of limestones of different ages. And here we see the distribution maps of electrical conductivity and sulfates. And by showing only the patterns, we can easily understand that the electrical conductivity increases from upstream to downstream and follows the distribution of the sulfates, pointing out that the electrical conductivity is mainly influenced by the sulfates, which is something expected in the area if we see that in this part we have the Triassic gypsum and the evaporites actually emerging in the area, cropping out in the area, affecting the whole chemical composition of water. Now, if we study further the chemical analysis, and I don't want to dive into details, I just want to show here again in this Piper diagram that all the fresh waters which are coinciding to the upstream of the area are plotted all together, and then we have another mixed group that comes from the evaporites of the area. So it is enriched, as we see from this diagram, in sulfates in related to the other group. And then we have in the lower part of the area some contribution of a different group of samples which do not come all together, so they are spread in this diagram. And actually also they are plotting differently than all the other two groups. So we see that the classification, the easily classified three categories, do follow the pattern in all the hydrochemical graphs. And when we examined isotopes, stable isotopes in the area, and actually we plotted oxygen with chloride and boron, we realized that these levels, so the upstream, midstream, and lower part, are also reflected here. And here we realize from boron that those samples that have also higher temperatures have also a deeper origin. And in this area, we also have a geothermal known field that they are trying also to use in the near future. So we easily see with major anions and cations, we can classify the different parts of the aquifer. And this can be done also with a rough distribution, actually, of the rare earth elements patterns for each level. And we see that we have three levels. The rare earth elements pattern is distinct for these three levels. Actually, it's resembling the upper part, and the lower part are pretty much the same and display an europium anomaly, positive one. And the middle part, what is distinct about it is that there is also a serum anomaly being present in the samples. So from this application, we were able to come to the conclusion to conceptualize the aquifer. Here we see the schematic Brock diagram of the aquifer. Those are the three levels, the upper, the middle, and the lower part. So we were able to separate three karst levels, identify the Richards mechanism of the area, which is actually the infiltration from rainwater. And we were able, together with water level maps, to delineate the aquifers and see where are their limits and how the faults create hydraulic barriers in the area. And investigate, of course, the origin and movement of groundwater, and gain a better understanding of the area. Now, in the same area, on another study, at the same time, actually, we collected samples to measure, to study the temporal variation of the chemical variables and the physicochemical variables. And we collected samples from different springs of high and low discharge, and springs that emerge from different geological formations, from different limestones of different ages, trying to understand better how the system works. And here we see the diagrams of electrical conductivity and temperature, and we see that every spring, and this is very clear, behaves in another way. And of course, we see some springs really having very short ranges, narrow ranges of electrical conductivity or temperature. And together with their temporal variations, the temporal variations of major anions and cations, we were actually able to draw conclusions on the behavior of the karst system, the way they behave during the recharge and recession period, to understand better what's the flow pattern of the karst system, whether we talk about conduits flow or fractures flow, the contribution of CO2, but also how the network, the conduit network, is configured. And we were led to these flow systems conceptual models for every spring. Each of the case studies that I mentioned are already published work, and I share the references at the end of my talk. Now, moving to trace elements, I'll give an example from an area in Greece where the tectonics is very intense and the geology quite complex. And here again, a basic classification of the different water types. Here we have two main water types, the fresh waters, and also the intermediate types that actually are a mixing of fresh water. Is fresh water being under the influence of the interaction with the rock? This is what we see. And we see that the main difference, again, is the sulfates in the area, which are enriched when it comes to the mixed group. Now, what we see here from the distribution of electrical conductivity and temperature is a zone in the central part of the area, which has lower temperature and lower electrical conductivity, which indicates actually dilution in the central part of the area due to the recharge from the main surface water bodies of the area. Now, another thing, as we see in the margins of the area, there are abnormally high concentrations of different trace elements. In this case, it's boron and lithium. Lithium is well-known trace element for deeper water. And we found out, I don't want to dive into details, we moved on and worked on this topic, but the interesting thing is that the faults of the area and the intersection of faults seems again to provide, to facilitate the emergence of fluids from greater depths in the area. What is very interesting from this work to be shown is the fact that along the main rivers, there are certain heavy metals present in the area, which are not related, of course, to the geology of the area, and are mostly related to anthropogenic activities. So we have high concentrations of lead and zinc along the beds of the rivers, pointing out to anthropogenic pollution. We know already that along these rivers there are industrial zones, and we see that during the wet period, so we also assisted ourselves with the piezometric maps, and when comparing with the piezometric maps, we realized that actually during the wet period, there is a contribution from the surface water bodies of the area. So this work led to the conceptualization again of the aquifer. We found out that during the wet season, we have communication between the different unconfined aquifers of the area, and they form a single aquifer, a uniform aquifer. We have contribution, again, during the wet season, we have contribution of streams to the aquifer recharge. We have the opposite situation during the dry season, but this contribution is confirmed by really high values of nitrates, nickel, lead, and zinc in the area along the riverbanks. We also identified a zone of intense recharge in between, in the central part of the area, which leads, of course, in dilution in the central part. And we identified and worked further later on 2 zones of deep circulation at the intersection of active faults in the area. Now, when it comes to gases, in the same area, since we realized that there is an interplay with the local faults, we tried to identify how CO2 and radon are fluctuating in the area. So what we see here, we have 3 main fault systems. So we have the Aegean system, it's this one. We have the Eliki system, and we have the Pyrgaki system. And what we identified was that along the Aegean fault and the Pyrgaki fault, we had an enrichment in radon dissolved in water. So we had values up to 8.2 kilobecquerel per cubic meter, really high values, while in a really active zone like the Eliki fault, we've seen the opposite. We've seen pretty much very low values. And this, looking to the literature, is explained due to the fact that other authors, other researchers found, other geologists actually found that this fault is sealed, all the fractures along the fault are sealed with clay minerals. So we concluded that indeed, in a really active tectonically area like this one, the fault zones can be depicted by the radon anomalies. And we also saw that even in the case that the faults are sealed, as in this case of Eliki fault, in this case, the radon emanation is prevented. So we have low values there. But radon proved to be a reliable tracer when it comes to faulted zones and fractured areas, and can be probably applied in areas where we are not sure about the tectonics or we are not sure about the existence of a fault. Now, another case study is a unique spring in Greece. We move along this area pretty much with the different examples. And this is a mineral spring. It emerges at the intersection of 2 faults, and it discharges a carbonate aquifer, which proved to be deep actually, and under reducing conditions. So it is a low discharge spring, but what's interesting about this spring is that during the wet period, during the high flow, it presents oil spill content. So we wanted to understand better what is going on with this spring. So we again plotted the samples. So what we tried to do is use a freshwater spring. So we sampled the freshwater spring every 20 days, and also the mineral spring every 20 days. And we tried to compare their behavior. And we see here that the freshwater spring, it is always calcium bicarbonates. While when it comes to Trifo spring, we see a shift from calcium to sodium. So we see a change in the water type, which coincides also with the oil spill in the area. So here, from the comparison between the trace elements of the thermal spring and the freshwater spring, we see that we have much higher lithium and gallium concentrations, and this is also true for barium and strontium concentrations. And if we have a look at the freshwater samples, these are not following the same trend. While here we see that we have the same patterns, which reflect something that reflects actually that those elements do have the same origin. So we see high values in the dry period, lower values during the wet period due to dilution. And we have high boron concentrations related, of course, to the evaporites in the area. from this work, we finally concluded that groundwater of the spring is of deeper origin than the freshwater spring. So due to the fact that we have high lithium and boron concentrations, and we have actually the increase of water level, which brings the aquifer into contact with the hydrocarbons pathway, and then we have the emergence of hydrocarbons in the spring during the wet period. Now, let's move to rare earth elements and their use. Normally, rare earth elements are plotted in graphs, and what we see in these graphs are the patterns, the distribution patterns, and these patterns normally of rare earth elements, as we've seen in the example of Luros, do show a unique distribution that normally reflects back the distribution of the rare earth elements in the parent rock, so in the host formation of the aquifer. In this case here, we used another approach. So here is an area which is in this part of Greece, in the central part. We are still in the central part, but we are moving a little bit to the east. Again, we see a tectonic actively area, which has actually 5 aquifers. We are going to focus on we focused on 4 aquifers: the coastal alluvial aquifer, the alluvial aquifer, the Mars aquifer, and the conglomerates aquifer. And here we have drawn the flow networks of this area. And then instead, first of all, we plotted, of course, the redox potential of the area, and we see different redox potential values for the different aquifers. So we see, for example, that we have high values in the conglomerate aquifer, and the Mars aquifer lies somewhere in between and has different behavior in parts of it. So in the western part, we have lower values. In the eastern part, we have higher values. But what's interesting here is, instead of entering the plots, the diagrams, and drawing the distribution patterns for this area, we decided to go with the spatial distribution and see what are we going to gain out of it. So we decided to plot the distribution of the total earth elements, and we found out that there is a separation, a distinction between the different values and the different aquifers. And also, we were able to check whether there is hydraulic connection where the aquifers intersect with each other. Now, other variables that are used when it comes to rare earth elements are the europium and cerium ratios. We plotted also those, and we moved a step further, and along these flow lines, we plotted the variables, different variables, physicochemical variables, but also ratios, and the rare earth elements, to the total rare earth elements, to see how is it changing, how every variable is changing along a flow line, which gave us actually a better understanding of the hydraulic relationship between the aquifers. And also, we figured out that the europium distribution has an inverse correlation with the cerium, but both of them are heavily influenced by the redox potential and pH values. We also found out that the ratio of europium is also correlated with the bicarbonates, indicating that the europium ratio increases, follows the carbonate ions, is influenced mainly by the carbonate ions in the area. So we were able to draw different and interesting conclusions. So we checked the relationship, and we understood better the relationship of the adjustment aquifers we realized that there are separate hydrogeological units and have different characteristics. We've seen a correlation of the redox potential and also the rare earth elements content of the parent rock with the rare earth elements content in groundwater. We clarified relationships when it came to aquifers one next to the other. And also, compared to the major elements, we found more distinct differentiation. So we realized that the rare earth elements can depict better what's going on in terms of hydrodynamic relationship of the aquifers, especially in areas where there are also human activities present. And another thing which is interesting as a conclusion from here is that in aquifers affected by anthropogenic processes, we have not affected by human activities, we have negative correlations of the correlation of the total rare earth elements and the redox potential. While when we have anthropogenic processes, this is not that clear in the area. So this is a good take-out message and something that we understood about the behavior of the rare earth elements in groundwater of the area. Now, moving to stable isotopes and ratios. Here, again, we used another pathway. Normally, what we do, we plot our oxygen values against altitude or the therium, and we try to understand whether there are evaporation processes, how our samples are aligned. In this case, we used the regression equation, and what we did, we calculated the difference between the mean recharge and the actual altitude, and actually these are the residual values, and this is what we plotted here, and we see that the higher values appear in the coastal area, while here we have lower values of this residual value. Now, we also applied tritium concentrations, and using different threshold values, we were able to classify the modern, mixed, and pre-modern age of the water. And we see here that modern water is the water from recharge, and recharge taking place from the carbonate aquifers of the area. So using isotopes in this case clarified the recharge mechanism, the hydraulic connections, and also gave an estimation of the residence time of different aquifers. Now, there are variables related to pollution, as I told previously, that we can use. And this is an example. We are again in the west part of Greece, and we have an area here and a spring that gives actually water to water supply of the area. But there was an issue here, and there were two incidences where there was high turbidity, high electrical conductivity, high iron and manganese in the well. And here we have some water level measurements plotted with the electrical conductivity and the rainfall of the area. And we see, after studying this spring and the behavior of this spring, that actually the aquifer, as we see here, for example, is very unstable hydrodynamically. So there is an equilibrium between the sea and surface water bodies that it is easily disturbed. So when we have overpumping, actually we have water entering the system from this Mars and seawater, and that's why we see the increase in electrical conductivity and turbidity in the system. So these incidences, since we are talking about the car spring, were only for a temporal, for a short period of time, but still created problems in the water supply. So the chemical variables in this case, along the hydrological year, confirmed the assumption that we have recharge actually taking place under overpumping conditions from the sea and the marshes of the area. Now, another interesting study, case study from Germany, again about pollution, has to do with a pesticide. And this is an area in Germany. It's Sohle aquifer in Germany. In Germany, this pesticide is already banned for almost 30 years, but still it is appearing, it's showing up in the groundwater. And we tried to study how this atrazine, this pesticide, actually reacts. And here we see the concentrations and the spatial, the places where we have the high concentrations in the area. And we tried to work on the temporal variations, but you see that the temporal variations are not following a particular trend. While when we worked with spatial distributions here, we realized that we have certain sources, point sources of this atrazine pesticide. So the atrazine persistence is highly dependent on hydrological and geological conditions. We've seen that the atrazine content varies within a hydrological year. We see that there is heterogeneity in the spatial aspect, which relates to water levels, chemical properties, and local geology. And we were able to identify a particular soil layer being responsible for this atrazine release, actually, and also draw the conceptual model of the aquifer based on the spatial distribution maps. Now, a last example that I'm gonna bring on the table relates to combined approach to study surface and groundwater interaction. This is a topic that gains traction at the moment because not many things are known when it comes to these interactions and how to quantify them, actually. So a case study from Germany, from Wüstebach catchment. It's a small catchment which is monitored, belongs to the Terreno observatory. Here we have a headwater stream, and we have some groundwater monitoring sites and also surface water monitoring sites. By plotting again the data from surface and groundwater, W is the surface water, G is the groundwater, we see that the samples can be classified actually into 3 groups, and they are enriched in sodium due to the salt from the de-icing of roads in the area. Moving on, we applied simple graphs, the Soler plots, that gave us an understanding using these ratios, the ratio between sodium and chloride. This Soler graph actually gives the distribution pattern of a sample. So each line is one sample, and we see that samples that do have the same distribution pattern also have the same origin. And here we see, for example, that certain groundwaters really relate to the surface water. And by performing high resolution EC measurements, we realized that there are sites where you have decrease of electrical conductivity relating to inputs from surface water, and also spots where we have increase of electrical conductivity related to input from groundwater. So we see that we have completely different concentrations, electrical conductivity in the surface and in the groundwater of the area. So by performing discharge measurements, we were able to quantify the contribution of groundwater in the area. The monitoring sites of groundwater are very limited. So we couldn't work that much with the wells. So that's why we worked along the stream. And we were able to calculate what is the electrical conductivity of the groundwater. Now, in order to be able to control more what is the inflows, where are the places of inflows and how they behave, we installed a DTS, a distributed temperature sensing device, which is actually a fiberglass, a data logger connected to a fiberglass cable. This is a technique used in oil and gas in the past years for the detection of leaks. This device can measure temperature every 25 centimeters, and the interval of measurement is 15 minutes. So here we see, okay, these parts, we see the raw data of this device. These dark blue parts are areas exposed in the water, but here we see differentiations of the temperature that relate to input from groundwater. So the data from the DTS, the distributed temperature sensing system, together with these charts and different other parameters, we use them as inputs for high flux model, and we were able to get to model the temperature at the downstream, at the outlet of this area, and the contribution of groundwater. So from this particular application, we were able to identify, first of all, the hotspots during the DTS. We combined the measurements with modeling, and we were able to quantify the groundwater fluxes. We have two ranges of electrical conductivity values, but actually we see that from the values of the stream, the shallow aquifer cannot justify these electrical conductivity values. So we assume, and we are working on proving, that there is a deeper contribution of more mineralized aquifer system, of an aquifer, a deeper aquifer with lower, actually, water temperature. So to wrap up my talk, hydrochemical tracers are extremely helpful in the study of all aquifers, not only the porous, but also the karst aquifers, as shown here. They are effective, especially when we lack data for an area, or where we don't have the density of wells, of monitoring wells to work with, like in mountainous areas or in deep aquifers, or in aquifers that are having a number of layers, and we don't know exactly the layer that we pump from. They enable the conceptualization of aquifer dynamics and provide information about the type of the aquifer, about the water circulation, and when necessary, of deep circulation, about the residence time, the recharge mechanism and patterns, the extent of the aquifers, but also its limits, the hydraulic connections and barriers between adjusted aquifers, but also the relationship that the aquifers can have with surface water bodies, the different flow types and configuration of conduit network and karst maturity when we talk about karst system, but also they reflect geological, tectonic, and other controls, such as land use, vegetation, mineralization, and recharge altitudes across the aquifer system. Thank you very much. And here are the references of this work. Thank you.
Thank you, Tina, for the very detailed presentation. All right, let's go to the question and answer segment. There is one question from Dr. Azhan. How to use hydrochemical traces to quantify the rate of recharge? So do you have an answer for that? Is it easy to quantify the rate of recharge using hydrochemical traces?
It's not easy, but it is possible. There are studies, for example, when it comes to radon, because radon is one of the emerging tracers because it's not abundant. So in surface water, for example, it's not abundant. So it is enriched in groundwater mainly. So, for example, the recharge rate, I was reading a publication the other day, calculating using radon concentrations, the input in a lake, the recharge of a lake from groundwater. So you need a tracer, actually, that is not abundant or is not reactive.
So
That's
you
why
need a
we
tracer
use
which is not
chloride, for
in.
example. That's why we use chloride in areas where seawater intrusion is not, the main issue. We use electrical conductivity to quantify, actually, these rates.
Okay, so you need something, some elements that is not abundant in the natural, so that you can easily trace it to quantify the
Yes.
rate of recharge.
Yes.
All right,
Yes.
fully understand. All right.
That's why I mentioned in my presentation that rare earth elements, for example, are more efficient than major elements just because they're not that common and reflect the geology rather than the human activities of an area.
So in the first phase of your presentation, you are using boron also as part of the traces. So is that because of the thermal evidence? Is that anything related to the thermal evidence by using boron? Is that also related?
Boron, actually, lithium is more related to geothermometers, as we call them. So there are graphs that can give you the depth. But boron is also many times related with deeper water circulation. But lithium is more related to temperature, and higher temperatures are related to abnormal geothermal gradient, as we say. So I see also a question that I'm trying to read here. So from a practical perspective, I take away the following application from radon can be used to map faults, for sure. It can be used, and actually to predict earthquakes. Another application. So I didn't show you all the applications of radon that I have worked with, but radon can really also predict earthquakes. Can determine if spring water is from fresh water is. The second one is not exactly this way. Can indicate, I would say, if there is input from surface water or groundwater, because they do have a distinct concentration of radon. Rare earth elements can be used to determine hydraulic conductivity. Yes, rare earth elements can be used to determine hydraulic connectivity. They can also be used to relate groundwater to the host rock. So if you don't know the origin of groundwater, if you draw the distribution patterns of rare earth elements of the rocks in the area, then you can easily determine what is the origin of this groundwater. It reflects the geology really well.
Great. Because in Malaysia right now, we are conducting rare earth element mining using in situ leaching (ISL). So it is also connected to the parent rock, of course, by drilling into the parent rock and extracting the REE using the in situ leaching. So is there any more questions? There is in one of your presentation, there is one slide showing that atrazine concentration limit is actually below the lower groundwater level period. Is it because the atrazine is heavier than the groundwater itself, or why does it happen like that?
Can you repeat your question? It is lower or higher during the wet or the dry period?
Yeah, I mean the graph that you draw, the atrazine limit, even lower than the lower groundwater level in the aquifer in Germany. Is it because is it heavier, or
I didn't show groundwater level. Wait a minute.
Is it the water level or in the aquifer?
No, actually, if you're talking about the distribution map and the graphs next to it, is how the atrazine concentration fluctuates along a flow line.
Along the flow line.
Yeah. So
All
we
right.
see that along this flow line, we have a decrease, a constant decrease, which points out to a point source.
A point
So
source. Oh,
yeah,
okay.
point source. So we don't have atrazine retained in all the soils of the area or the whole aquifer. No, we have hotspots of atrazine relating to a specific type of soil of the area.
And since 28 years ago, and half-life of atrazine is what? Still inside the aquifer. Yeah.
And actually, in many countries of the globe, atrazine is still allowed.
Oh, is it? Oh, okay.
Yeah. So that's the interesting case. And 30 years after the ban of atrazine in Germany, they cannot get rid of this pesticide.
Yes,
So
yes.
we have to be a little bit careful with the different chemicals. But even even a substance that was not supposed to be in groundwater can be used as a tracer if you know it's.
Yes, correct. Like the pollution, like the atrazine. Yeah, correct. Do we have more question from the floor? Anybody wants to ask question from Miss Tina? How about the forever chemicals right now? Is it valuable to use as a tracer?
Which one?
The forever chemical PFAS. So is there any tracer research
Actually,
using PFAS?
my expertise relates to using natural tracers
Natural
that you
tracers.
find in water to gain some insight about the geology, the groundwater movement, and all these aspects that we
Yeah.
work as geologists, I would say. I always say we are not chemists, but we can use chemistry to make assumptions and confirm our assumptions when it comes to groundwater movement.
Right. Yes, I remember there is one well where we have a quartz fracture, and the water also smells a bit of like hydrogen sulfide. So we believe that there is some thermal contact for the quartz zone from the fracture. But that was in Slim River. So there is also one of the tracer, good hydrochemical tracer, natural. Yeah. Do we have
So
more questions?
I'm
Yeah.
also
Okay.
open. Yeah, I'm also open to contact any of you. Anybody can contact me in case that you have questions or you want to apply tracers in any area and you have some additional questions on how to work with it.
Yes. So if there is no more question from the floor, I would like to thank Miss Konstantina for giving us such a very detailed and knowledgeable presentation today. Thank you again, Konstantina. And hopefully we can meet again in the same platform. Any last word from you?
No, thank you very much for the invitation and the opportunity to talk about the past years of research in different countries. Thank you.
Great. Okay, so let's end the webinar right now. Thank you, everybody. And for Malaysian geologists, you can fill up the form for CPD hours.